My name is Ranjit Kumar. I am from ECE Section B. Today is my topic about observation of crystal lattice plant in neutron and ion bombard J invented paper. Let's dive into the video. In first slide we can see introduction to crystal lattice planes. In crystal lattice planes, we can see the study of crystal lattice planes provides insights into the structural changes in materials. Like example, we can see germanium is a semiconductor that exhibits unique properties under neutron ion and ion bombardment. Understanding these changes is crucial for advancements in semiconductor technologies and material science. We can see in the diagram there are six examples, which is like 100, 010, 001, 100, 010, and finally 001. Let's see in the second slide, we can see background on germanium. Germanium is a metal and is a element symbol called as Ge. Germanium is a group fourth element with a diamond cubic crystal structure. Its electronic properties make it a key material in this field of electronics and optoelectronics. Bombardment process can significantly alter its physical and chemical properties. You can see in the picture the structure of the crystal structure of germanium. This is about the background on germanium element. Next slide we can see is neutron bombardment effects. In neutron bombardment introduces displacement damage in the crystal lattice of germanium, and this damage can lead to the formation of vacancies and interstitials in the crystal structure. Like vacancies means the empty spaces of crystal structure of germanium, and the extent of damage can be qualified using techniques such as X-ray, diffraction, and electron microscopy. In this figure, we can see projectile particle and displaced atom. In next slide, we can see ion bombardment mechanism. In ion bombardment mechanism, involves the collision of energetic ions with the germanium lattice. This process can result in a range of defects, including point defects and amorphization. The energy and type of ions used influence the resulting structural changes significantly, like modulus, intensity, planes, or atom in planes, like these mechanisms. This process can result in a range of defects. There are more defects in this process or in this mechanism. Let's dive into the next slide. Characterization techniques. Characterization techniques are various techniques are employed to observe and analyze crystal lattice planes in bombard germanium or germanium. Sorry, transmission electron microscopy, which is called as TEM, enables detailed imaging of the defect structures, and X-ray diffraction, which is called as XRD, provides information on the crystallinity and orientation of the lattice planes. This is total about the characterization techniques of these, and you can see these observations from neutron bombardment. We can see in the figure what we has x, y, z axis. There are more axes to be found in that figure. This is called as neutron bombardment leads to specific patterns of lattice destruction observable in diffraction studies. The degree of destruction correlates with the neutron influence and temperature during the bombardment. Results indicate that neutron includes defects can enhance the material's electronic properties. Let's dive into the next slide. Observations from ion bombardment. In ion bombardment results in unique defect structures that differ from those seen in neutral bombardment. In this figure also we can see the total bombardment mechanisms. The creation of cluster defects can be observed affecting the electronic behavior of germanium, which is called as fourth group element in periodic table. Comparative studies show that ion bombardment can induce more severe damage than neutron bombardment. There are more differences between the ion and neutron bombardment. Let's dive into the next slide. Implications of for semiconductor applications. Understanding the nature of defects helps in tailoring the properties of germanium for specific applications. Enhanced defect control lead to improved performance in electronic devices. This research has implications for the design of next generation semiconductor materials. In this implementation for semiconductor application, we can see the classification of defects in crystalline solid. In this we can see defects in crystal. There are four types of defects in crystalline solid. There are point defect, line defect, and third one is surface defect, and last fourth one is volume defect. In first point defect we can see vacancy vacant sorry vacancy interstitial substitutions shortly frankled, and in line defect we can see edge and screw dislocations. In line defect we can see more dislocations, we can observe that. In surface defect we can see grain boundary and twin boundary. Last one, volume defect. Wide crack jet is the main defects in the whole semiconductor applications. Future research directions. This is very important for our lives because in this we can see the more job securities and data privacy like that. Ongoing studies aim to explore the effects of varying bombardment conditions on germanium is very important. Future investigation is needed to understand the long-term stability of the defects produced. The integration of advanced characterization techniques will provide deeper insights into the crystal behavior. This is about the future research directions. We must follow the future research directions because it is very helpful for us. And finally, conclusion. We can see the graph which is growing up like in straight way. The observation of crystal lattice planes in bombard germanium reveals significant structural changes. Both neutron and ion bombardment have unique effects that are critical to semiconductor technology. Continued research is essential for harnessing these effects in practical applications. We can more see in the practical applications because we will we will bombard each other, and it reveals the germanium into the structural changes. Thank you.